In this video, we're going to learn how to calculate an equilibrium constant if we're given the initial concentrations in an equilibrium and one of the final concentrations. And this is a really powerful technique we're going to use throughout the next few chapters in this course. So here we go. We're going to start with an equilibrium. So A in equilibrium with B, and we're going to jazz things up here. We're going to have one A in equilibrium with two B's. And we're going to be told the initial concentration of A, and we're going to write that as 1 mole per liter. Okay, we're going to use a little subscript 0 to represent time 0. So at the beginning, so the beginning concentration of B is 0 moles per liter. And at equilibrium, we're going to know the concentration of just the one thing. And so maybe the equilibrium concentration of A is 0.75 moles per liter. And so the question is, can we solve for the equilibrium constant? And the answer is, you bet we can. And this is going to introduce ourselves to what we call an ice chart. And this is the first time we've seen it, but it won't be the last time we've seen it. And in an ice chart, what we do is we start with the equilibrium and we place it at the top of this chart, and we lay down 3 rows that we call I, C, and E. And I stands for initial, and C stands for change, and E stands for equilibrium. And we can use either moles, we can use moles per liter, or we can use partial pressures to fill out our ice chart. So we're free to use any one we like. Because we're dealing with Kc and because we're dealing with concentrations, we probably want to use moles per liter throughout. But if for some reason we were given moles, we can still use them. We just have to be a little careful. So we start out with the initial concentration of A at 1 mole per liter, and we have no B. And now we have to fill out the ice chart. So on the change line, what we need to do is pay attention to the way the chemical equation is written. And right now it's written so that every time one A gets used up, 2 B's get formed. And so in the change line, we can write minus X for A, and under B, we can write positive 2X. So now why are we writing X's? Well, we don't know the change yet, but we know that whatever this goes down by, this will go up by double the amount. So this is negative because the change is going down. This is positive because the change is going up. And in an ice chart problem, we simply sum together the initial and the change. And I'm going to be a little bit sloppy here and leave off the units. I'm going to write this as 1 minus X. And over here, this is going to be 2x. So at the bottom line, this is what I have. Now, if I know the value of x, I can solve for the equilibrium constant. So what would the equilibrium constant be? Well, Kc is the equilibrium concentration of B all squared divided by the equilibrium concentration of A. And at the bottom line of my ice charts, I'm giving everything I need here. The concentration of B is 2x. Okay, I need to square it. Concentration of A is 1 minus X, and again, I'll play loose and fast with significant figures here and just write it like so. So if only we knew what X was, we could solve this. So now we look at this problem here, and we see that we're given the equilibrium concentration of A is 0.75 molar. So that tells us that this value here, 1 minus X, must be 0.75 molar. So if 1 minus X is 0.75, we can sort of do by inspection and tell that X must be 0.25. And so now we're ready to plug it into this expression here. So for Kc, it is equal to 2x, so it's 2 times by 0.25. That's a half, all squared, divided by 1 minus x, so 1 minus 0.25. So that is 0.5 squared over 0.75. And if we do the math, that comes out to be 0.33. So the equilibrium constant for that reaction is 0.33. That was pretty fun, huh?